All right, guys, we are starting our last chapter of chemistry, so you've almost made it through. So this last chapter is on chemical equilibrium. It's chapter 16. And so to this point, when we learned about chemical reactions, we've learned about them moving in one direction. When actually, I wanted to stick my hand in here so you can see that I'm here. But we've learned the reaction to go in one direction. So we have a reactant plus a reactant. So we have, for example, we have carbon monoxide, which is a gas, plus nitrogen dioxide, which is a gas, and they react to form carbon dioxide, which is a gas, plus nitrogen monoxide, which is a gas. Doesn't fit very well. All right, now that's how we've learned this reaction to this point. But chemistry is not that simple. So believe it or not, what you've learned so far through the year was actually simple compared to what really happens in nature. So what this chemical equilibrium talks about, we're going to learn how actually things don't just happen in one direction. They actually happen going back and forth. They go back and forth between reactants and products. All right. So a more accurate representation of what this reaction would be to say, all right, these two, carbon monoxide plus nitrogen dioxide, make carbon dioxide and nitrogen monoxide. But it also, once more of the products are formed, then the reaction can go in reverse. And so carbon dioxide and nitrogen monoxide can also react to form these. So some reactions will actually go in either direction. It will go reactants to products and products to reactants. And those reactions are said to be equilibrium reactions. All right. And so we have a forward reaction. Okay, so the forward reaction is just the reactants that you put together, move forward to make the products. The reverse reaction is when the products then react to form the reactants. All right. Now, when you combine those two, all right, so if both of these are happening at the same time, then our new rate equation can be drawn, let's say reaction rate, okay, and time down here. Okay, so taking into account, so remember our reaction rate and time before, it was something like that, or it was, when you have the activation energy, something like that, but it was always just one thing going in one direction. All right. But with the equilibrium reactions, taking into account both, we now have a forward reaction. All right. We have the reverse reaction, and they hit a point where they're happening in both directions at the same rate. Okay. And so you reach a point where you don't have, it's not moving in that direction or that direction. They're both happening at the same rate. And that would be the equilibrium. Okay, once we get to whatever this time is, okay, in this reaction, assuming that we're not adding any reactants or products to it. If we just put two things together, allow them to react, it will get to a point of an equilibrium reaction. We'll get to a point where the reverse and the forward reactions are happening at the same rate. And so it flattens out the line. So that's the forward reaction. This is the reverse reaction. Okay, I would be familiar with with that chart, all right, with that graph, all right. So again, reaction rate. So you're starting out with your reactants over here, okay. So what this graph shows us is with the forward reaction. So here is where we put our reactants together. They're up here, okay. It's moving forward, but as these are being used up, Now we have more products as we go forward in time, and so the reverse reaction starts ramping up in the rate of that reaction. So what the reverse reaction is actually increasing as the forward reaction is decreasing, which makes sense because we're using these up. These are getting lower in concentration. These are getting higher in concentration. So these are going to start reacting more. These are going to start reacting less till they get to the point where they're reacting at the same rate, which is right here. And at that point on, there's no push in one direction or the other. All right. Now, there is experiment 16.1. You can do that experiment or you can read it, and most of us know it's a simple experiment. So if you have the things in your house and want to do it just to see it visually, then I would say by all means do that experiment. But what I'm going to do is I'm going to move ahead to the Comp Check 1 on page 486. All right. And it says a chemist is studying a reaction, measuring the rates of the forward reaction and the reverse reaction. Here's the data collected. So you look, so the table it looks like it's 6 columns, but really it's 3 columns, and instead of having 6 rows, they just brought the other 3 rows over so it wouldn't take up so much of the page. But so if you see at the point, so it says, at what point did the concentration of reactants and products stop changing? All right. Well, you see that at 5 seconds, the forward rate is higher than the reverse rate. At 25 seconds, it's still the case, but they're getting a little bit closer. 45 seconds, they're getting closer. At 65 seconds, they are both at the same rate. So once they hit the same rate, they are at equilibrium. And so that is the point where that reaction hits equilibrium. So there won't be a push to go in the reverse or in the forward direction at that point. So at 65 seconds. All right, so I want to go over how to calculate the equilibrium constant and go over a couple pieces of information that are really important about the equilibrium constant. So in the last chapter, we learned about the rate constant. All right, and we learned, some things that make the rate constant different from other constants that we learned are that the rate constant is only the constant for a certain chemical reaction. Okay, so there will be a different rate constant for one reaction versus another. Okay, so that's where constant is not the term that we're used to associating with something that changes. So that was one thing about the rate constant. It changes per reaction, and also the units of the rate constant could change. All right, and so what we're going to learn about the equilibrium constant is the same things. All right, so there's something that's similar to the rate constant, and there is a difference between the rate constant and the equilibrium constant. All right, so let's first look. We have our typical equation. We have A plus B makes, now this is equilibrium, and I made the full arrow before the way I like to do it, and this is just me. This is what I did in college, but you can make the full arrow, or it just was faster for me to go up and then go down, and that shows that it's the same thing. All right, so C plus D. Okay, so that's the reaction we're used to seeing with the hypothetical situations, or for the general situations. Now, the constant, the equilibrium constant, it is also notated with K. Okay, K is the concentration of C. Okay, raised to the C power, and this is at equilibrium. Okay. And then it's times D raised to the D at equilibrium over A raised to the A at equilibrium times B raised to the B at equilibrium. Now, the first thing that you'll notice with this equilibrium constant is, remember, the rate constant did not use the coefficients. right? The rate constant was the order. This was X and Y up here, so it was the order of reaction with respect to a product or a certain product or reactant. All right, so when we have the equilibrium, we're back to using the coefficients. So balanced equations are important. I will tell you through this chapter, if you're doing any of these equilibrium constant calculations, you're not going to have to balance the chemical equations. So the coefficients should already be there for you, but you just need to make a big note that the equilibrium constant does use the coefficients in front of the molecules in the reaction, whereas the rate constant that we learned in the last chapter did not. Okay, so that's a big thing. All right, so that's one way that they are unlike. Okay, so the equilibrium constant uses these. The rate constant did not. What makes them similar, though, is because these are exponents too, the units. The units can be different. Okay, so that's what makes the equilibrium constant and the rate constant similar, is the units aren't always the same. You don't always have, it's not always going to be, 1 over molar squared times S. It could be molars cubed. It could, it depends on what the coefficients are. Okay, so the main way that they are not alike, the equilibrium constant versus the rate constant, is the equilibrium constant does take into account stoichiometry and the rate constant does not. The way that they are similar is the units can be different. Okay, they can change depending on what the reaction is. So those are how they're similar and how they're different. Now I want to do example 16.1 in the book to finish out this video. All right, I should have left that equation on there. But, so 16.1, we say a chemist performs the following reaction starting with, okay, so we have 2NO plus 2H2, and I'm going to make my 2 arrows, makes N2 plus 2H2O gas. Make sure when you're writing these equations that you do absolutely put the phase in, because it is vitally important later on in the chapter when we are calculating. Actually, it doesn't account for it yet, but yeah, the phase is taken into account when you make the calculation for the equilibrium constant. And depending on what phase it is, it may or may not be included in the calculation. So you have to make sure that you always put the units in, because it matters in this. All right. So it says, starting with 0.1 molar of the nitrogen monoxide and the hydrogen. Okay, so those are the two reactants. And it says at equilibrium. So we have the concentration. This is 0.100 molar. This is 0.100 molar. Okay. And then at equilibrium, the concentrations of NO and H2 are 0.024 molar. So 0.024 molar, and this is at equilibrium. And this one is also 0.024 molar at equilibrium. All right, and let's see, so N2 at equilibrium is 0.038 molar, and that's at equilibrium. And then the H2O is 0.076 molar at equilibrium. All right, now what we need to first know is when they say that the concentration of nitrogen monoxide and hydrogen are at 0.1 molar, okay, That's extra information that we don't need to know. It doesn't mean you don't have to write it down. You can write down, I want you to get in the habit of writing down all the given information, and then you can look through it and see what you need. But remember that our rate calculation is the concentrations at equilibrium. These two were not at equilibrium, so we don't need to account for those. Those are not going to be included in our rate constant calculation. All right, so we had, remember our calculation, our equation for it was we start with the products on the top, right? So we have 0.038 molar, okay, and there's a 1, there's assumed to be a 1 in front of the N2, so that's just going to be 1. You don't have to write 1, but I'm just writing it to show that we have 1. And then it's going to be multiplied by 0.076 molar, all right, and there's a 2 in front of that, so that's going to be squared. Okay, our bottom is going to be, we have 0.024 molar, and that has a 2 in front of it, so we have a 2, and that's going to be multiplied by 0.024, molar, and that's also squared. We have a 2 in front of it. Okay, now we do all that math. Okay. But before we do the numbers, I want to just look at our units. So we have m to the first power times m squared. So we're going to add those, all right? So that's going to give us, in the numerator, we have m third and to m to the third, okay? For the denominator, we're going to add these two. So we have m to the fourth, right? And so when we have this, we don't have our numbers yet, but we can cross these out if it's, that leaves us with 1 m on the bottom, right? We take 3 of those out, 3 out from the bottom, that leaves us 1 in the denominator. So our final unit is going to be 1 over molar, all right? And you can see how that's dependent on the coefficients, right? If these were different, we'd have different crossing out. Okay, and so that's our units. And then if you do all this math, type it into your calculator, you get 660. Okay, and that equals our equilibrium constant for example 16.1. All right. So